Hey everyone, it's Eddie Does Math here with the hardest questions you'll see in Algebra 2.
Let's start it off with inverse functions. So an inverse function, we want to set the x into a y and the y into an x. So we'll have x is equal to y over 2y minus 1. And now we solve for y, and that will give us f inverse of x. So here, I want to multiply both sides by 2y minus 1. That gives me x times 2y minus 1. That'll be equal to y since the 2y minus 1 has canceled out on the right side of the equality. Now, after we distribute, we get 2xy minus x is equal to y. And since I want just one of the y's by itself, I'm going to move everything to one side that has a y. So I have 2xy minus y is equal to x. I can factor out this y now just to get one y by itself. And once I divide both sides by whatever's in the parentheses here, I will get y is equal to x over 2x minus 1. And that is my inverse function. And if you notice, something really cool happened here. My inverse function is the same as the original function we started with. That is what we call an involution because it is already symmetrical about the line y equals x. So something really cool here with inverse functions. Next, we have exponential equations, one of the hardest topics, including logarithms as well, but I chose to do exponential equations for this video. Let's take a look at this one. We have 3 to the 2x minus 5. There's not much we can do with that. However, on the right side, we recognize that 9 and 27 are both powers of 3. So we're going to try to make everything on the right side of this equation something with a base of 3. And when we do that, we can start off by saying, well, 3 squared times 3 cubed x to the power of negative 1/2. This negative 1/2 came from the square root being in the denominator. When we flip it about the division bar, the exponent becomes negative, and the square root can be rewritten as the power of 1/2. So there it is, and now we want to combine all these together. So if 3 to the 2x minus 5, we can combine the 2 and 3x. That becomes 2 plus 3x to the power of negative 1/2, and we can multiply these out. So that becomes 3 to the power of negative 1 plus 3 halves x, and this is equal to 3 to the 2x minus 5. Recognize that the bases are the same, so the powers must be equal to one another, and so that's what we do. We set the powers equal to one another, and we can slowly start to see the light in this problem. After we subtract 3 halves x from both sides, I'm left with 1.5, not 1, but 0.5x. I was going to say 1/2. After I add 4 to both, or 5 to both sides, I get a 4. Getting ahead of myself. My mouth is working faster than my brain here. And I'm going to multiply both sides by 2. X is equal to 8. And yeah, that's it for this problem. Rational equations, when we solve for x, first we have to identify our domain whenever we have variables in the denominator. Our domain will be everything where x is not equal to negative 2 or 1. Because if x is equal to negative 2 or 1, then we have zeros in our denominators. Can't have that. We can't divide by 0. So right off the bat, we already know that these two x values will not work. However, we do recognize that this denominator right here factors into x plus 2 times x minus 1. And that's exactly the other denominators that we have. So what we can do here, something really neat, is we can get rid of all the denominators by multiplying by x plus 2 times x minus 1. So let's take a look at what happens with this first fraction. The x plus 2's cancel out, leaving just an x minus 1 times the numerator of x. Moving on to the next fraction. X minus 1's cancel out this time, leaving just an x plus 2 times the 3x plus 1. And the final fraction, we're just left with a 4 because the entire denominator cancels out with these two factors. Now let's distribute. We have x squared minus x is equal to 3x squared plus x plus 6x plus 2 plus 4. And all I did was I foiled out, foil first, outer, inner, last, or some teachers say to just distribute completely, and that's what I did here. Let's combine all like terms. So when I subtract x squared from both sides, I get 2x squared. I add an x to an x plus 6x. That's going to be 8x. 2 plus 4 is 6. This is equal to 0. Now, all three terms have a common factor of 2 that I can factor out. I'm not going to need that 2 there anymore because anything times 0 is going to be 0. That 2 will not be important in this problem any longer. So I factor this out. I get x plus 3 times x plus 1, and that's how we know x is going to be negative 3 or negative 1. Thankfully, neither of these x values are within our domain, so That's it. X is equal to -3 and -1 are our answers. Now, talking about rational equations, we can also look at rational functions and analyze them to oblivion. So let's start with state all the vertical asymptotes or holes in the graph. Vertical asymptotes occur when the denominator is equal to 0 and that factor itself does not cancel out with the factor in the numerator. So let's factor these out first. The numerator is a difference of squares factored into a binomial times its conjugate. On the bottom, we can factor out just like this. Notice how none of these factors cancel out. So holes in the graph, there are no holes in the graph for this function. However, we do have some vertical asymptotes. Those vertical asymptotes will be x is equal to 6 and x is equal to -2. This function cannot have x equal to 6 and x equal to -2 because that will give us a 0 in the denominator. So vertical asymptotes, check. Horizontal asymptotes can be found by looking at the highest powers on both the numerator and denominator. That's x squared over x squared. Now look at the coefficients. They're the same, 1 over 1. So that's how we know our horizontal asymptote will be y equals 1. Later in calculus, you'll learn that we can just take a limit as x approaches infinity of any rational functions like this to find the horizontal asymptote. But for now, you look at the degree of the numerator and denominator. If they're the same, you take the coefficients, put them over one another, and that will be your horizontal asymptote. Boom. X-intercepts. The first thing you should think when you see the word x-intercept or 0 or root, any one of those, you know that y is equal to 0. And when y is equal to 0, you set the numerator equal to 0. So x squared minus 9 is equal to 0. Well, we factored it already up here. So we know x can be 3 or -3. So those are our x-intercepts, 3, 0 and -3, 0. Keep things simple. All right, our last one involves de Moivre's theorem. De Moivre's theorem. I'm not exactly sure how to pronounce it, but we all know it because we've dealt with complex numbers before in Algebra 2. Let's take a look at this. We're given something in complex form. We want to change it into polar form first in order to use de Moivre's theorem. So r will equal the square root of 3 squared plus 4 squared. And this is very familiar because, 3, 4, 5 triangles, we're going to have just, excuse me, a 5 here. And that's r. So now, when we want to put things into polar form, we also have to find theta. And theta is just going to be inverse tan of b over a. So we have -4 over 3. But we know that 3 minus 4i is in the fourth quadrant. And because we're in the fourth quadrant, we can rewrite theta as negative inverse tan of positive 4/3. And that's what we'll be using for theta. Now we know z then will equal 5 times cosine of theta plus I sine of theta. Theta being negative inverse tan of 4 over 3. Now, given this, we can apply de Moivre's theorem. We can say z to the 5th will be equal to 5 to the 5th times cosine to the 5th theta plus I sine to the 5th theta. So we're just taking everything to the 5th power here. Ooh, I actually made a mistake here. Instead of to the 5th power, it should be cosine of 5 theta and sine of 5 theta. Okay, now from here, I need to solve for cosine of 5 theta and sine of 5 theta. Now you can choose to plug this into a calculator, but we do have some trigonometric identities that we can use here. We know that cosine of 5 theta is equivalent to 16 cosine to the 5th theta minus 20 cosine cubed theta, and then at the very end, I believe it's plus 5 cosine theta. Now from here, I can plug in what cosine of theta is, or what cosine of theta would just be 3 over 5 using our little triangle here in the fourth quadrant. We know this is 3, this is -4, this is 5, and this is our theta. So cosine of theta will be 3 adjacent over 5 hypotenuse, adjacent over hypotenuse. So once we plug this in, 3/5 to the 5th minus 20, 3/5 cubed plus 5 times 3/5. Plug this in and you get actually a pretty nice fraction compared to a very messy decimal. You get -237 all over 3125. We can do something very similar with sine of 5 theta. It's going to be the same equation up here, except the cosines will be sines. And this will equal 3116 over 3125. I have a little cheat sheet on the side here, so I didn't have to plug this into a calculator again. So now plug these back into here, and something really cool happens. 5 to the 5th is actually 3125. So we have negative 237 over 3125, and you can already kind of see what's going on here. We'll have I times 3116 over 3125. Notice that the 3125s will all cancel. So z to the 5th is actually just equal to negative 237 plus 316i, which is very, very cool.
If you enjoyed this video or learned something new, make sure to click the subscribe button and check out the description below for links to my courses. See you soon.